Welcome everyone, and thank you for joining us for today's webinar, Teaching with Microwaves. My name is Sean Suggett, and I'm a Technical Sales Representative for CEM Corporation. Just a bit of housekeeping before we begin. If you have any questions during the presentations, please go ahead and type them into the GoToWebinar control panel. We will have time to answer all questions at the end of the presentation. This webinar will be recorded and will be available to view on CEM Corporation's website following the webinar. Now, I'd like to turn the mic over to our presenter, Gabrielle Thalhammer, the CEM Life Science Marketing Specialist. Gabrielle?
Thanks, Sean, and welcome everyone to our webinar today. I'd like to talk to you about the benefits of integrating a microwave into your undergraduate laboratory and talk to you also how easy it is to optimize and expand your current curriculum with a microwave. So just to start off, I'd like to do a quick overview of Microwave 101 for those of you who might be unfamiliar with this kind of technology. So what is a microwave? A microwave is a form of electromagnetic energy that falls at the lower end of the electromagnetic spectrum and consists of an electric and a magnetic field. So the electric field in red is capable of transferring heat to a substance, while the magnetic field in blue has minimal interaction. So microwave photons are lower energy sources and are comparatively low in energy relative to your typical energy requires for molecular bonding and breaking bonds. So this means that microwaves do not have enough energy to affect molecular structures directly, and any microwave energy absorption is a purely kinetic effect. So no molecular bonds are broken when microwave energy is applied. There are 4 available frequencies for industrial, scientific, and medical applications allowed by government regulations. So the most common frequency used is 2,450 megahertz, and is preferred because it has the right penetration depth to use with laboratory scale samples. It's also pretty convenient and cost effective, as there are common available power sources to generate microwaves at this frequency. So your home microwave has a magnetron that produces this particular frequency. So microwave heating is a very different process from conventional heating, so like an oil bath or a hot plate or a Bunsen burner. Microwaves couple directly with the molecules that are present in your reaction mixture, not with your reaction vessel. So this results in instantaneous selective heating of anything that will react to either dipole rotation or ionic conduction. So these are the 2 fundamental mechanisms for transferring energy from microwaves to a substance. Dipole rotation, on the left-hand side of the graphic, is an interaction in which polar molecules try to align themselves to that electric field we mentioned before. The rotational motion of these molecules as it tries to orient itself with that field results in a transfer of energy, or friction, and thus heat. There are a number of factors that will ultimately determine your dipole rotation coupling efficiency. However, any polar species, so your solvent or substrate, that are present will encounter this mechanism of energy transfer. Again, this is a direct energy transfer to any polar species, so you do not need bulk amounts of solvent to transfer that energy like you do in conductive methods, which means most microwave procedures require little or even no solvent sometimes. If a molecule is charged, then the electric field component of the microwave moves ions back and forth throughout the sample. This movement is called ionic conduction, so this is on the right side of the graphic, and this also generates heat. The electric field generates ionic motion as the molecules again try to orient themselves with that electric field. The temperatures of the substance also affects ionic conduction, so as your temperature increases, the transfer of energy becomes more efficient. So now that we know what a microwave is, how does it compare with conductive heating? So let's say we have a reaction vessel placed on a hot plate, and we're trying to heat that reaction to a specific temperature. This is a form of conductive heating, so energy is transferred thermally through conductive currents. If you've ever sat and waited for a pot of water to boil, you know this is a very slow mechanism. Energy must first be transferred from the hot plate to the container, then work its way through the reaction mixture to drive that reaction forward. So this energy must then somehow be removed at the end to stop any chemical transformations. This can be challenging, especially when you're dealing with higher temperatures. You may need to put your beaker in an ice bath and simultaneously stir it to get that mixture to cool down. So you're also at risk of unwanted side reactions during that slow cooling process. Now let's look at the same reaction and vessel in a microwave. With microwave heating, energy transfer is direct and rapid to individual components in that reaction mixture. So keep in mind that each component in the reaction mixture has a slightly different polarity or ionic conductivity, meaning that some will absorb energy more efficiently than others. So we'll take a look at that in a few minutes. So this direct molecular activation means the vessel is not used as a mode of intermediate energy transfer, like it was when it was being heated on a hot plate. Microwave energy also has the additional advantage of being able to be instantly on and instantly off. Once the microwave is turned off, the application of energy stops immediately. CEM microwave systems also feature a programmable reaction quenching step at the end of your radiation cycle, so reducing those unwanted side reactions and increasing the purity of your product as the reaction mixture is brought back down to room temperature in a very short period of time. So in this example, we have a reaction vessel with a polar solvent, so let's say methanol, and two reactants of about equal concentration with different dipoles. When microwaves are applied, you'll notice that the reactants will absorb some energy, but the majority of the energy is absorbed by your solvent. So this phenomenon is known as bulk heating and is the quickest way to reaching your desired temperature. But what if we don't have a polar solvent? What if we have a non-polar solvent like toluene in our reaction? So we know that this reaction will be difficult to heat based on the solvent, but remember we do have those other components within the reaction that can be selectively heated. We do have the same two reactants of about equal concentration as before, but now we've added a metallic catalyst. So metals can go in a microwave, but they have to be submerged and they have to be at low concentrations. You'll see that when we apply microwaves, the catalyst will absorb most of the energy and the solvent won't absorb any. So stirring is very important for creating and maintaining a homogeneous heating profile throughout the reaction mixture. Without stirring, hotspots can occur in areas where the catalyst may have settled in your vessel, which can possibly damage your vessel, and it's highly likely that your reaction will result in a low yield. There are a couple different types of scientific microwaves available on the market today. The single-mode microwave is designed to allow one standing microwave inside of the cavity, so this creates a high homogeneous power density. It does limit you on your sample size, however, based on, again, the cavity size. The single-mode microwaves are ideal for sequential reactions at smaller scale, so about less than 75 milliliters. Multi-mode microwaves are a lot like your standard home microwaves. These have variable cavity sizes and allow multiple standing waves inside of the actual cavity. These typically also have higher magnetron powers, but you also have less field homogeneity. And what this means is when you have multiple microwaves bouncing around inside of the cavity, you do have the potential for hot and cold spots. And the real way that you get around this is by stirring your sample and also rotating your sample inside of the cavity. Multi-mode microwaves are ideal for parallel reactions and also scale-up reactions. So there are a lot of benefits with introducing a microwave into your classroom, but one of the biggest ones is definitely going to be time savings. Oftentimes you'll have reactions that go for an hour and a half to 3 hours where students are sitting around waiting for reaction to reflux and they're really not doing too much. So what a microwave can do is it can speed up some of these lab procedures, giving them less time just sitting around and giving you more time to actually teach your students. These reactions are also more efficient, so you can teach students some of the green chemistry principles of like better atom economy, reducing your energy requirements, and choosing some of your solvents, and so on. The microwave will also help you create a safer teaching lab. You're eliminating the dangerous Bunsen burners and oil baths, also some less toxic solvents, and a microwave is much easier to set up and use. Microwaves also have the ultimate reaction control, so you can program several different parameters such as time, temperature, pressure, and power to create reproducible results every single time. So if you hand an experiment to your class, each one of them, if they prepare the reaction properly and they put it in a microwave, should be getting the exact same results every single time. Microwaves also allow you to expand your curriculum and introduce those green chemistry concepts that I mentioned before, and also give students a new opportunity with research. And microwaves are affordable instruments. This is a multi-purpose piece of equipment that can be used for teaching and research and for a wide variety of different applications. So this isn't just for organic synthesis teaching. This could also be used for inorganic, materials science, digestions, environmental labs, and so on. CEM, in conjunction with Nicholas Leadbeater and Cynthia McGowan, has developed an undergraduate teaching manual that has several different organic chemistry experiments that you can integrate into your curriculum. So here are some examples of experiments that we have in the laboratory manual. We started with the standard reflux conditions that are used in most organic chemistry lab classes and optimized them for microwave heating. You notice that the standard reaction conditions call for refluxing on average for about an hour. You can also see that the hydrolysis and aldol condensation experiments require quite a bit more time than a standard lab class is allotted, which could prevent some instructors from ever considering these experiments for their curriculum. So using a CEM microwave system, we were able to complete each of these lengthy experiments in just under 15 minutes per run. So imagine being able to have students prepare their reactions, run their methods, and get started on analysis of their samples all within the first 30 minutes of class time. Shorter run times will also give students time to repeat their experiments if they need to. Accidents happen, and often there isn't enough time in the class to repeat reactions. So instead of giving partial or even no credit to a student who may have made a mistake, a microwave will give students a chance to repeat their experiment for a chance at full marks. You'll also notice that different solvents were used for the microwave optimized reactions. So let's look at the Diels-Alder experiment at the top. Under standard reaction conditions, this is a run using DMF, which is a fairly toxic and expensive solvent. But after optimizing the method, we're able to perform this reaction at a lower temperature in less time using water as your solvent. So all around a shorter, safer, and greener reaction. The CEM laboratory manual is only one resource for microwave experiments. There are a slew of ACS journal publications where educators like yourselves have published microwave-assisted experiments and full course curriculums for organic, inorganic, and analytical chemistry lab classes. The Journal of Chemical Education and Journal of Sustainable Chemistry and Engineering are a couple I would highly recommend. There are a few customers I met who have gone a step further and have utilized a microwave for high school outreach programs and also for advanced research courses in undergraduate level. The advanced courses challenge students to identify a problematic chemical transformation and utilize green chemistry practices and instrumentation like a microwave to optimize. So a class like this will give students a different approach to learning and also allows some instructors a bit of freedom to explore new fields. Nearly any conventionally heated synthetic transformation can be adapted for microwave heating. The power of microwave radiation has been harnessed in nanomaterial assembly, polymerization reactions, small molecule synthesis, and radiochemistry, but it's also compatible with air-sensitive reagents and transition metal catalysts. Modern microwave reactors like the Discover SP can safely maintain high-pressure atmospheres, so reactions can be performed at temperatures that exceed your reflux temperature, expediting your reaction rates and reduce your reaction times. So how do we optimize some of our current methods to be run in a microwave? So reaction optimization is not too difficult. You can explore new solvents or even less solvents or even no solvent. You can vary reaction time and play around with your temperatures. So to demonstrate the modification of a conventionally heated transformation to microwave heating, let's look at this Heck reaction with iodobenzene and methyl acrylate. So under conventional heating protocols, the transformation is limited to 80 degrees Celsius, the boiling point of acetonitrile, and it takes about 20 hours for completion. Just not exactly ideal for the time-constricted undergraduate laboratory course. So we have three parameters we can work with: solvent, temperature, and time. So a solvent, we can try a different solvent, maybe with different microwave absorbing properties, or even no solvent. Temperature, we can increase or decrease, but I would recommend starting with a conventional temperature. And then also time. So a 10-minute reaction time is fairly common with microwave synthesis. We'll start with that while we're optimizing our temperature. So as we expect, 80 degrees had a pretty low conversion to our product, so about 13%. So we adjusted our temperature up about 40 degrees per run to provide an efficient manner to identify our optimal reaction temperature. At 120 degrees Celsius, we saw 44%, and 160 we saw 79%, so we are increasing as the temperature is increasing. However, when we got to 200 degrees Celsius, the conversion increased to 85%, but we did see a significant amount of byproduct. So we reduced it down to 180, seeing similar results, and backing it back down to 170, we saw that high level of conversion with minimal level of product formation at about 82%. So now that we've established that 170 degrees is our optimal reaction temperature, we can look at other parameters like time. So we use the PowerMax cooling feature and a fiber optic probe for temperature measurement in our Discover SP, and we noticed that extending our reaction time out to 15 minutes did not improve our conversion to product, and it increased our byproduct formation. So we backed down to 5 minutes, and we saw that we had comparable levels of yield and purity to our 10-minute reaction. Lastly, we're able to look at solvent optimization. So acetonitrile is a moderate microwave absorbing solvent and is already proved pretty effective for this transformation. So try a nonpolar solvent like toluene, and we saw a dramatic decrease in our reaction conversion, so it's about 25% compared to 82%. We performed the reaction neat, however, and saw a significant increase in our product conversion to 93%, while maintaining minimal production of byproduct. So upon purification, the product alkene was isolated in an 87% yield. So there you have it. With some minimal optimization, we were able to convert this 20-hour reaction to a 5-minute neat method in the Discover SP microwave system. The lack of solvent and low energy requirement makes this a perfect example of the application of green chemistry principles to a common reaction. So don't worry, a detailed overview of converting conventional methods to microwave methods is available in the form of an application note on the CEM website. For those of you listening in right now, you can download the document through GoToWebinar. CEM is proud to offer unlimited application support via email or phone, and our applications team is ready to assist with any questions you might have about optimizing any methods you found. Now let's take a look at two of CEM's microwave instruments that can be easily incorporated into a classroom. So the Discover SP is an ideal system for smaller class sizes of about 12 students or fewer. This sequential synthesizer allows students to prepare reactions at a variety of scales using our two standard reaction vessels. So these vessels cover a working volume range of about 200 microliters up to 25 milliliters and use a simple silicone cap and septa. So no tools are necessary to seal the vessels either, just prep, cap, and run your method. The Discover SP is also equipped to run atmospheric reactions using standard glassware like a round bottom flask, up to 125 mils in volume. Running open vessel reactions allow access to the rapid heating capabilities of your microwave while giving users the flexibility to add additional reagents or remove aliquots during a running method. Variable speed magnetic stirring is a standard feature for all Discover SP systems as well. The Discover SP self-tuning cavity adjusts for your changing chemistry, meaning that as your reaction progresses, the microwave is able to adapt to the new chemical environment and adjust the microwave power accordingly. So automatically adjusting the power is an efficiency feature, which will save energy and reduce wear on your system's magnetron. And so this adaptive behavior also means you create a safe working environment and you get reproducible results every single time. Safety is always a concern in teaching labs, which is why there are several embedded safety features in the Discover SP to ensure your students and lab are protected. The intuitive software and ActiVent pressure device comes with the temperature and pressure release limits, which protect users from exposure to vented gas and hot vessels. The cooling feature I mentioned previously ensures the vessel is at a safe temperature for removal at the end of your reactions. If an accident should occur, all debris is contained within the cavity and can be cleaned up in a matter of just a few minutes. Just simply remove the spill cup, clean up your mess, and you're ready for another run. No tools necessary. The Discover SP is also the most flexible system on the market. So while you might be interested in using the microwave for a laboratory course, you can also use it for your own personal research. And again, you're not limited to using it for the organic chemistry department alone. This is a multi-purpose system that can be utilized for inorganic, materials, environmental, and biochemical applications. There are several accessories that can be added to Discover systems for customization. So an autosampler can be added to increase your throughput during a class, or you can set up reactions to run overnight. A cavity camera can be added to assist with reaction optimization or provide pictures and videos for publications. Something that's really cool is as your reaction progresses, you can watch for a color change or precipitant or something crystallizing and adjust your methods accordingly. There's also accessories for adding gaseous reagents, performing subambient reactions, flow chemistry, hydrolysis, and some large-scale reactions. The main safety feature of the Discover SP that I want to touch on is the ActiVent pressure device. As you can see in this video, gaseous byproducts may be formed during some reactions as your temperature increases. The silicone cap I mentioned previously aids in relieving this pressure buildup by allowing gas to escape in a controlled manner out the back of your instrument, away from users. So venting can occur at pre-programmed pressures while the method is running or when the safety limits of the system have been reached. So by automatically relieving the gaseous byproducts, the silicone caps and the pressure device minimize overpressurization. This significantly reduces our vessel failures and allows your reactions to reach higher temperatures. The caps offer a safe seal without the need for crimping tools. The Mars 6 synthesis microwave is a multi-mode microwave system ideal for parallel reaction processing under uniform conditions, or scale-up chemistry. The ability to run multiple reaction vessels simultaneously is advantageous for larger class sizes, so maybe more than 12 students or if you have pairs of students, where sequential synthesis might not be as time efficient for your class. Like the Discover SP, the Mars 6 can accommodate pressurized vessels and standard laboratory glassware for atmospheric reactions. Temperature for these batch reactions is measured in what we call the control vessel. All reactions on a vessel carousel should be exactly the same, so a fiber optic probe is inserted into one vessel for temperature monitoring. For analytical chemistry, an IR temperature sensor is also used to monitor temperature in the vessels, but for our purposes, a fiber optic probe is used. There's a simple touchscreen and software that features guided method programming and training videos for proper vessel assembly, system operation, and routine maintenance. Reactions, run data, and methods can all be recalled easily and exported onto a USB drive or printed from the built-in printer option. Like the Discover SP, the Mars 6 doesn't limit your chemistry applications. There are multiple reaction vessel options for various applications and scales, with pressure ratings able to accommodate high pressure generating reactions up to 800 psi. You can choose from Teflon or glass vessels for small or large scale. Variable speed magnetic stirring is a standard feature in all Mars 6 synthesis systems and is highly recommended for any synthetic reaction. The custom-engineered microwave cavity of the Mars 6 synthesis is constructed of high-grade solid steel with a heavy-duty spring-mounted door with safety interlocks. So should an accident occur, students are out of harm's way as the incident is contained within the cavity, and the instrument will turn itself off to prevent any further damage. The most common vessel set that we see in classrooms is the GlassChem vessel set. This set comes with 24 or 36 easy-to-assemble 3-part vessels. Students just need to prepare the reaction, insert the Teflon plug, then tighten the Teflon cap. Each vessel is placed in a numbered sleeve, and the whole carousel is placed in the microwave. A method's programmed, and bam, you're done. After your reaction is finished, the system will cool the vessels down to a safe temperature for handling. If you're using the CEM Organic Chemistry Lab Manual, this is the vessel set that we reference for all the Mars 6 synthesis versions of the experiments. However, those experiments can be modified for different vessel types. And with that, I want to thank everybody for joining us today. If you have any questions, you can send them over for us now or email us at synthesis.support@cem.com. Please remember to look at the handouts for this webinar for a sample of the Clean, Fast Organic Chemistry Lab Manual and some of the application notes I referenced. For more resources and product information, please visit the CEM website at cem.com.